Hello everyone. In today's video, I will discuss about AVL trees. Okay. So what are your AVL trees? Okay. So AVL trees are basically your binary search trees. Okay. So these are your binary search trees. Okay. But these have one more features that these are your height balanced. These are your height balanced. Height balanced binary search trees. Okay, height balanced binary search trees. So now binary search trees you all know now. Okay, I have already discussed. So see, binary search trees, you know that in binary search tree, the if this is your root node, this is the left subtree, and this is your right subtree. Fine. So in binary search tree, what you know is that the elements or the nodes of left subtree should always be smaller than your root node, and root node should be smaller than your right subtree. So in this way, all the elements go in your binary search tree. Okay. Now AVL trees are your binary search tree, but these are your height balanced binary search tree. Now what do you mean by this height balance? See, height balance means that the left and right height of your tree should almost be equal. Okay, the height of left subtree and right subtree should almost be equal. Fine. Now how we will measure this, that these two heights are almost equal? So see, one more term called your balance factor. Okay, your balance factor comes into picture in your AVL trees. Fine. Now what is this balance factor? So see, balance factor is your, it is your height of left subtree minus height of your right subtree. Fine. So balance factor is your this, and this value should always be either -1, 0 or 1. Fine. Now you see this. See, you have to calculate in AVL trees, you have to calculate this balance factor for each and every node of your binary or each for every node of your tree, and that is your height of left subtree minus height of your right subtree, and that value should be either of these three values, either -1, 0 or 1. So if this balance factor is either of these three value, then your tree is balanced. Okay, then it is your AVL tree. But if for any node the balance factor is not either of these three value, then your tree is not balanced tree, or it is not your AVL tree. Fine. Now see, now we will first of all see that why your balance factor should be either of these three value only. Okay, so see, let us suppose a tree. Let us suppose I am having a, okay, let us suppose I am having a tree. Okay, I'm having a binary search tree. Okay, now see, to be AVL tree, it should be height balance. Now what I told, what is height balance means? Its left and right height should almost be equal. Now see, in almost, what comes? See, almost means it should either be equal, almost, actually equal, exactly equal. So when it will be exactly equal means it will have equal number of nodes in left subtree and equal number of nodes in right subtree. Then only the left and right height is exactly equal. And for that, see, for that balance factor will be what? See, balance factor is height of left subtree. So height of left subtree minus height of right subtree. So both when heights are equal, then height of left subtree minus height of right subtree will be your 0. Then you will get the balance factor as 0. Fine. And I said almost equal. So when exactly equal, then your balance factor is 0, because see, height of left subtree minus height of right subtree, both are equal values, both are equal heights, then it will be height of left subtree minus height of right subtree is 0. But it can be one less or one more also, means height of left subtree can be 1 more than height of right subtree. Okay, now it has 3 nodes, so height of left subtree is your 1, 2, 3, and right subtree is your 1, 2, so 2, 2. So 3 minus 2 is your 1. Okay, so 3 minus 2 is your 1. So now see here only the height of left varies by only one node. Okay, so this it can be a little more, okay, by having one node more, or it can be little less also by if your right subtree height is one node more than this one. Okay, now what will be your balance factor for this node? Height of left subtree, so height of left subtree is 1, 2, so this will be your 2 minus height of right subtree is 1, 2, 3, 2 minus 3 is minus 1. Now see, you can have this value also, and when it was 3 here and 2 here, then 3 minus 2 was your 1, so this one. So we have balance factor these three values because at 0 we are having both left and right height exactly equal to each other. In minus 1 we are having right height little, or we can say 1 greater than this left tree. Okay, so because the balance factor is the height of left subtree minus right subtree, so this value is smaller than this, so 2 minus 3, then we are getting minus 1, and when your left height is 1 more than your right height, then it is coming 3 minus 2 equals to 1. Okay, so only these three can be your balance factor for a tree to be balanced or height balanced binary search tree. Okay, so for every node the balance factor should be either of these three value. Okay, then only your tree will be balanced. Fine, now see, we will see how we will find the balance factor for each and every node. Okay, so let us suppose I'm having, okay, I'm having one binary search tree like this. Okay, so if this is your 5, okay, this is your 3, then this is your 7, and then this is your 6. Fine, now this is your binary search tree. Now how we will find the balance factor for each and every node, that we will see. Okay, so first of all I want the balance factor for this node. From leaf node we will start. Okay, so balance factor for this will be height of left subtree minus height of your right subtree. Now height of left subtree, left it does not have any child, right also it does not have any child, so 0 minus 0 will be a 0 as your balance factor. Now coming to this node, see, now height of left subtree, left it has one child, so height of left subtree is your 1 minus height of right subtree, so right it does not have any child again, so 1 minus 0 is your 1, so balance factor for this node be your 1. Now coming to this node, so again height of left subtree minus height of right subtree, but it is a leaf node, it does not have any child, so left height 0 minus right height 0 will be a 0 again. Okay, now for this node, height of left subtree, so what is the height of left subtree? 1 minus height of your right subtree, so height of right subtree is 1 and 2. Okay, so 1 minus 2 is your minus 1. Okay, so after calculating the balance factor for every node, at every node you have to check that either at this point it is balanced or not. Okay, so see, first of all when we have calculated 0, yeah it is balanced, then 1 is also in this range, so it is balanced, again minus 1 is also in this range, so this is balanced, 0 is again in this range, so this is your balanced binary search tree till now, or it is your AVL tree. Fine, because these all the balance factor is in this range. Okay, now let us suppose if you have one more node here. Fine, let us suppose you have any one more node here. Now again we will find the balance factor for each and every node. Okay, so now see, balance factor for every node will change now. Okay, now this is your leaf node, so height of left subtree minus height of right subtree, it will be your 0. Okay, now for this node, height of left subtree height is your 1 minus right subtree 0, 1 minus 0 is your 1. Fine. Now for this 7, see, height of left subtree. What is the height of left subtree? 1, 2. 2 minus height of right subtree. So height of right subtree is a 0. So 2 minus 0 is a 2 here. Okay. Now you can check at this point and this point, it is balanced. But see here, 2. So 2 is not in your this balance factor range. So here your tree got unbalanced. So now this is not your AVL tree, or this is not your height balance tree. Fine. So in this way we have to calculate the balance factor for each and every node, and we have to find that whether our tree is balanced or not. Okay. So see, I will take one example and we will see that what are the possibilities when your tree is not balanced, and then what are the steps we have to follow to make our tree balanced. Fine. Okay, so let us suppose, I have three nodes, 1, 5 and your 7. Okay, so these are three nodes given, and we have to construct different, or we can say unique binary search tree which are possible from these three nodes. Okay, so how we will insert these nodes? So first of all, see, if first I am inserting the node in this manner only. Okay, I have 1, 5 and 7. I have to insert the node in this sequence only. Okay, so now what will be your binary search tree? See, this is your 1. Fine. First of all, first is your root node. Now 5. 5 is your greater than 1. So where it will come? It will come to the right of 1, because this is your binary search tree. Okay. So see, 5 I will draw on the right of 1. Now 7 will come. 7 is again greater than your 1. So it will come on the right of 1. Then it is again greater than your 5. So it will again come to the right of 5. So 7 will come here. Fine. Okay. Now see, this is the first way. If I want to insert this node in the second case, see, 157 I have taken. Now if I reverse this, if I want to insert in 175, okay, so if I am taking the nodes in the order, your 1, 7 and 5. Fine. Now how the nodes will come? See, 1 is your root node. Okay. Now 7. 7 is your greater than 1. So it will come to the right of 1. Fine. Now next node is 5. So 5 is greater than 1. It will come to the right of 1. Then when it will come here, 5 is less than 7. So where it will come? It will come to the left of 7. So 5 will come here. Okay. So one possibility is this, and this is your different binary search tree, different from this. Okay. Now third, if I take the nodes in the order, 157 I have taken, 175. If I will take 5 in the front, so if I will take 5, 1 and 7. Okay, now how will your tree will be? Okay, so see, 5 is your root node now. Okay, now 1 is smaller than 5, so where it will come? It will come to the left of 5. Okay, and now 7. 7 is your greater than 5, so it will come to the right of 5. Okay, now again if I take the nodes in the order, okay, 5 and 7 I have taken. If I am taking the nodes in the order 5, then 7 and 1, if I will interchange, then this will be 5, 7 and 1. Fine. Now how your tree will be? See, 5 is your root node. Now 7. 7 is your greater than 5. So 7 will come here, and then 1 is your less than 5, so it will come to the left of 1. But see, these two trees are same. Okay, so these two are not your unique binary search tree. These two are same. Okay, so one case we will neglect from here because both are coming the same. So I will take this one. Okay, now because first of all we are seeing that how many unique binary search tree we can make from our three nodes. Okay, Now one more, what other possibility we can take? See, 157 I have taken, then 175 interchange, 517, 571. Now if I will take 7 in the front. Okay, so what is the possibility? Fourth. What is your fifth possibility? See, if I take the notes, 7, then your 1, and then your 5. Fine. Now how will your tree be? See, 7 is your root node. Okay. Now 1 is your smaller than 7. So it will come on the left of 7. Okay. Now see again 5. 5 is smaller than 7, but it is greater than your 1. So it will come to the right of 1. Okay. One possibility is your this, again different. And one more possibility is your, if you will take the notes in order, 7 1 5 I have taken, if I will take 7 5 1. Okay, 7 5 and 1. Okay, now see, 7 is your root node. Okay, now 5, where 5 is less than 7, so it will come to the left of 7. Fine. Now 1 is smaller than 7, and it is your smaller than 1, smaller than 5, so again it will come to the left of 5. So now these are the 1 2 3 4 5, because these two are same. So 5 different binary search trees you can make from 3 different nodes given. Fine. 5 different and unique binary search tree. Okay. So see, now we have a direct formula also. So if you have n nodes given, okay, so number of different unique binary search tree possible from n nodes, the direct formula is your 2n factorial upon n factorial into your n plus 1 factorial. Okay, so one direct formula is this also. Okay, so now if I will put here our n equals to 3, so see how much we will get. If n equals to 3, then 3 to the 6 factorial upon your 3 factorial into your 3 plus 1 4 factorial. Okay, now if I will solve this, so the 6 will be your 6 into 5 into 4 factorial, you can write. Okay, and this 3 factorial is your 6 into 4 factorial, I am writing as it is. Fine. Now see, this 4 factorial and this will be cut, 6 and 6. Now what is your answer? 5. Okay, so from when n equals to 3 I have taken here, then 5 different unique binary search tree are possible. And see, 1 2 3 4 and 5, we have also got 5 different binary search tree. So here, because n was a small number, we can try by a trial method, by seeing that what are the different possibility. But if n a large number is given, then you cannot find by a trial method. Okay, so sometimes in exams this can be directly asked for n equals to a big number, that how many different binary search trees are possible. Okay, how many different unique binary search trees are possible, then you can apply this formula at that time directly. Fine. Okay, now see, now I have got different 5 binary search tree, but now what I have to check is these are our AVL trees also or not. Okay, these are our binary search tree, but now are these our height balance binary search tree or AVL trees? Are they are AVL trees or not, that we have to see. Okay, now for finding the AVL trees, what we have to check, we have to find the balance factor for each and every node. And if balance factor is within our the range, what is that, either 0 -1 or 1, then only it is our AVL tree, otherwise it is not. Okay, so we will see here. So I will, this is also not okay. Okay, so your balance factor should be either your -1, 0 or 1. Okay, so we have to check here that each node is having this balance factor or not. Okay, now see, I will start from this one. So see, this is your this is your leaf node. Now what is the balance factor for this node? Height of left subtree minus height of right subtree, that is your 0. Okay, now for this node, height of left subtree 0 minus height of your right subtree, that is 1. So 0 minus 1 is your minus 1. Okay. Now for this node, height of left subtree. What is the height of left subtree? 0. So 0 minus height of right subtree 1, 2. Okay. So 0 minus 2 is your minus 2. Now you check the balance factor, that either all the balance factor are in this range or not. See, 0 is fine, minus 1 is fine, but now minus 2 is minus 2 is either of these values? No, it is not. So here your tree got unbalanced. Okay, so because of this node, because of the balance factor, because of the balance factor of this node, your tree is not balanced here, or this is not your AVL tree. So this is your binary search tree, but this is not your AVL tree. This is not your AVL tree. Okay, now see, we will check this one. Again see, the balance factor for this node is your 0, leaf node. For this node is height of left subtree 1 minus 0, height of right subtree is 0. So 1 minus 0 is your 1. For this one, height of left subtree is your 0 and height of right subtree 2. So 0 minus 2 is your minus 2. Now again check the balance factor is in this range or not. Okay, so see, 0 is in this range, 1 is this range, but minus 2 again, because of this node balance factor, again this is not your AVL tree. Again this tree is not your AVL tree. Fine. Now we'll move here. Now see, for this tree, balance factor for this will be 0, because height of left subtree minus height of right tree. For this again 0. Now for this one, height of left subtree 1, height of right subtree 1. So 1 minus 1 is your 0. So now for this it is also again 0. So now see, the balance factor for all the nodes is within this range. So this tree is your AVL tree. Okay, this tree is your AVL tree. Now 1, 2, 3 we have checked. Now for this one, see, balance factor for this node will be 0. This is a leaf node. For this one will be height of left subtree. Height of left subtree is your 0. 0 minus 1 is your minus 1. For this node, height of left subtree is 1, 2. 2 minus right subtree is 0. So 2 minus 0 is your 2. Okay. Now again see, 0 is fine, minus 1 is fine, but 2 again, this is not your correct balance factor. So again, this is not your AVL tree. This is not your AVL tree. Fine. Now see this one. This is 0. This is your 1 minus 0 is your 1, and for this one 1, 2. 2 minus right subtract 0. So 2 minus 0 is your 2. Now again see, this is fine, but again this is not fine. So again this is not your AVL tree. Okay, now what we have seen, among the 1, 2, 3, 4, 5 binary search trees possible, only this is our AVL tree, but the rest 1, 2, 3 and 4 trees are not your AVL trees. These are your binary search tree, but these are not your AVL trees. And now why these are not your AVL trees? Because the balance factor for a certain node, like for this one, for this node the balance factor is minus 2, which is not in our range. Because of that it got unbalanced. Okay, now see what we call these types of problem. Okay, so see here, see, we will write this as your R and R. Okay, because both are on right side. So these type of problems we will call as your RR problem, but these will be called your RR problem. Okay, problem we are having because tree is not balanced, but because of which problem? This is called your RR problem. Now what we can write this node? See, we can write this. This is your right side. This will can write R, and this is left. We can write this RL. Now this problem is called your RL problem. This problem is called your RL problem. Okay, the third one, this tree is your balance. Fine. Okay, this we will draw this. Okay, so this was your AVL tree. This was fine. Okay. Now this one, see what we can write for this one. See, this is your left side, so this we can write L, and this is your right side, so we can write this as R. So this problem we will call your LR problem. LR problem. Okay. Now this one we can write this because both are on left, so we can write this LL, and this problem will call your LL problem. So this is your called LL problem. Okay, fine. Now see how many problems we are having. First of all is your RR problem, one problem. Another one is your RL problem, second. Then third is your LR problem, and fourth is your LL problem. Fine. So we are basically having four types of problem when your tree is not balanced. Okay. RR problem, LL problem, RL problem, and your LR problem. Okay, so now we will discuss these four types of problem in detail and the solution for it. Okay, because of these problem your tree is not getting balanced. Now we have to solve this problem so that our tree will become our balanced your AVL tree. So we will discuss all the four types of problem one by one, and we will see the solution also for it. Okay, so that the tree will become our balance. Okay, so see, first one was, if I take the notes in the order 1, 5 and 7. Okay, so now how was your tree? See, 1, then is your 5, and then is your 7. Okay, in this way only you will have notes. Fine. And what we have written for this is, these both are our RR. So this problem was called our, what was this problem? This was your RR problem. Fine. This is your RR problem. Okay. Now why we are having this problem? Because see, balance factor for this was 0, for this was 0, minus 1, and this for this was 0, minus 2 is your minus 2. Now see, because we are having the balance factor for this node as minus 2, because of that only this tree was your not your balance. Now see why you are having this no balance factor as your minus 2. See why you are having minus 2, because for this balance factor will be height of left subtree minus height of right subtree, but in the left you are having 0 child. Okay, and in the right you are having 2 children, so 0 minus 2 is your minus 2. So see here, in the left you are not having any children, but what we have told that height balance to your AVL tree is your both left subtree height and right subtree height should be almost equal. Okay, it is should either be exactly equal or almost equal. That is, it can differ only by one height. But see here, the height is 2 and here height is, it does not have any child on its left side. Because of that only we are facing this problem. Okay, but if I will have some child in the left also, if I am having some child in the left also, okay, then what will happen? Then the difference of height will be equal, because if I am having at least one, see if I am having one, so 1 minus 2 will be your minus 1, then this tree can be balanced. So what I will do to solve this problem is, I will rotate this tree in this left side, because left it is not having any children. But if I will rotate this tree left, then what will happen? One node will come to the left and 5 will become your root node. See what will happen if I will rotate it to the left. Okay, so see, this is your 5. Okay, this will, see if I rotate, now 1 will pull down and 5 will become your root node. So this tree will become 5, then is your 1, and then is your 7. In this way only your tree will become. See, 5 will go as the root node, 1 will come down, and 7. Okay, so you will get this tree. Now what you have to do, you have to check that now either your tree is balanced or not. So for that we have to calculate the balance factor for each and every node. So now balance factor for this will be 0, for this will be 0, and for this will be 1 minus 1, 0. Now the balance factor is in our range. Our range was your -1, 0 or 1. Okay, so this was your range. Now our balance factor is in this range. Now our tree is balanced. So what we have done in our RR problem is we have done the left rotation. We have done our, which rotation we have done here? Left rotation. Okay, so we have performed the left rotation and we have got this tree, and now this tree is our balanced tree. Okay, so now first case was this. Now our second case, see, if I take the nodes in the order 7, 5 and 1. Okay, if I will take the nodes in this, now how our tree will be? See, 7 is our root node, 5 smaller than 7, 1 again smaller than 5. So in this way we have got the tree, and here the nodes are on our left and left. So this type of problem you are calling as our LL problem. LL problem. Okay, fine. Now why this problem was there? Because see, the balance factor for this node 0, balance factor for this node 1, 1 minus 0, height of left minus right is 1, and for this one height of left subtree 2 minus 0 is 2. So because of this node, because the balance factor for this node is coming 2, because of that our this tree is not balanced. Now see again why this is 2, because what is the balance factor? Height of left subtree. Left it is having 2 children, but right it does not have any child. So our tree is not balanced, because tree balance should be both left and right height should be almost equal. So what we want here? We want some children in its right side, so that our tree can get balanced. So to get the children in the right direction, we have to rotate this tree on its right. All the children are on the left, so we will rotate this tree on the right, so that now our tree will become, see how our tree will become. If I will rotate this right, 7 will come down, and now again 5 will become your root node. So your tree will be 5, 7 will come down, and 1 will be on the left. Now what you have to do again? After every rotation, you have to calculate the balance factor for each and every node again, to check whether now it is balanced or not. So see, for balance factor for this is 0, for this is 0, because these are leaf nodes. Left minus right 0, left minus right 0, 0 minus 0. Now for this is 0, 1 minus 1 is your again 0. Now this is your balance tree. Okay, so now what we have done here is we have performed the right rotation. Here we have performed the right rotation. Fine. So these were the two types of problem. What was the third problem we were having? See, if I am having the nodes in the order 1, then your 7, and then your 5. Okay, so if I am having the nodes in this order, so see 1 is your, okay, so 1 is your root node. Now 7 is greater than 1, so it will come on the right of 1. 5 is greater than 1, so it will come to the right of 1, but is smaller than 7, so it will come to the left of 7. Okay, so now here what we were at, this is your R, this is your L. So this problem is your, what is this problem here? RL problem. Fine, this is your RL problem. Now for RL problem, what we can do? See, again, see here, the balance factor for this will be 0. For this is 1 minus 0 is your 1, and for this is 0 minus 2 is your minus 2. Fine, because of this node, our tree is not balanced. Now see, in the RL problem, what we will do first? See, we have to make these problem either RR or LL. Okay, so see, R is here. Now this L, we will make it R. Okay, so see, these two nodes, first we will perform here rotation on these two nodes. So these two nodes are on the left side, so what we will do, we will perform right rotation on these nodes first. Okay, now see, when we will perform right on this, or we will move it to right, okay, so what will happen, 5 will come here above, 7 will come here down. Okay, so after a right rotation, this tree will become 1. Then when you are moving it to the right side, 5 will come above and then come here 7. Okay, fine. This way only it will come. See here, if you will perform right rotation on these nodes, 7 will come down and 5 will go here above. Okay, so what we have done here, we have performed your right rotation. We have performed the right rotation here. Okay, now after every rotation, what we have to check first, we have to find the balance factor to check that either now your tree is balanced or not. So see, balance factor for this node will be 0, for this will be 0 minus 1 is your minus 1, and for this node will be 0 minus 2 is your minus 2. But again, our tree is not balanced here. Okay, so now what does it mean? Again we have to perform rotation on it to make it balanced. But now see, this was your R before only, now this is also your R. Now when you have RR means you have RR problem, then what rotation you have to perform? In RR problem, what rotation you have to perform? Left rotation. Now again you will perform a left rotation on this tree. Okay, so after left rotation, what this tree will become? See, if you will move this left, now 1 will come down and 5 will become your root node. So how your tree will be? See, 5 will be your root node, 1 will come here and 7 will come here. Fine. Okay. Left rotation, 5 will become your root node, 1 will come down and 7 will be here. Okay, now see, what is this rotation now? For RR problem, you have to perform left rotation. You had perform here left rotation. Now again what you have to do after rotation? You have to check the balance factor for each and every node. So balance factor for this is 0, for this is 0, for this is 1 minus 1, again your 0. Fine. Now is your tree balanced or not? Yes, your tree is balanced because all the balance factor 0 are 0 and that is in our balance factor range. Fine. Now your tree is balanced. So now in this tree, in your RL problem, you have performed two rotation. First of all your right rotation and then is your left rotation. Fine. Okay, now our fourth problem. Okay, so see, and one more thing I will tell you here. See first. See, but in this rotation, okay, in this RL problem, sometimes what we can do a mistake is that, see, what I have told you, that you have to perform a rotation on it and you have to make it RR problem only, because this was RL, so R was here previously only, so we will make this also as RR so that we can perform it as a left rotation. Now sometimes what we will do is, okay, what I instead of rotating it completely, what we will do, we will simply stretch it like this. I have to make it RR, so what I will do, I will say, okay, this is our RR. I will simply stretch this 5 as here. Okay, that we have not to do, because see, this is not even your binary search tree also. See, 5, see, 7 is greater than 1, fine. But 5 is your smaller than 7. So it should have come to the left of 7. But see, here it is on the right of 7, 5. Okay. So this is not your binary search tree also. So don't simply stretch it like this, 7 to 5 like this to make it RR. You have to do proper rotation, okay, and move this 5 above and 7 down like this. Okay, so this mistake please don't do. Okay, like simply stretching it 5 here to make it RR. Never repeat this problem. Okay, you have to do a proper rotation and make it like this. Okay, so this mistake you should not do. Fine. Now see, what was our fourth problem? If the nodes are your 7, 1 and 5. See if the nodes are in this order. So 7 I will insert here, then 1 is smaller than 7, then 5 is smaller than 7 but greater than 1, so it will come like this. Fine. Now the balance factor for this will be 0. For this will be your 0 minus 1, that is your minus 1. For this will be 2 minus 0, that is your 2. Okay. Now again, because of this node, because of this balance factor, our tree is not balanced, and we were writing this as, because this is left direction, this is L and this is your R, so we are writing this as your LR problem. Okay, so this is your LR problem. Now in LR problem, what we have to do, see, first of all, see, this is already your L. Okay, this is already your L. Now you have to make this also L, because if this will become your L, then it will come your LL problem, and in LL problem you have to directly perform a right rotation to make it balance. But this is not your LL, this is a LR. So first of all, we'll perform a rotation on these two nodes and make it your LL problem. So if I want to make it LL or make a left rotation on this node, okay, so then how our nodes will be, see, if I will move it like this, rotate, 5 will come above and 1 will come down. So see how your tree will become, this is your 7, okay, this 5 will come above, so this is your 5 and this is your 1. Okay, in this way only your tree will be. Okay, now this was your L, now this is all will also become your L. Now which rotation you have performed here first? Your, which rotation you have performed here? Left rotation. You have performed the left rotation first. Okay, now again after a rotation, what we have to check? Balance factor. So see, balance factor for this node is your 0, for this node is your 1 minus 0 is your 1, and for this node is your 2 minus 0, that is your 2. Again your tree is not balanced. Okay, so again we have to perform a rotation here, and now see, this is your LL. So what we have to perform here? We have to perform a right rotation, because all the nodes or the left subtree is on the left side only, but I want some nodes on the right also, so that our this tree will get balanced. So I will perform a right rotation. Now on performing right rotation, 7 will come down and 5 will become your root node, so the tree will become your 5. Okay, 7 is coming down, 7, and this is your 1. Fine. Now again what you have to do? Find the balance factor for each and every node. So this is your 0, this is your 0, and this is again 1 minus 1 is your 0. Now the balance factor for every node is your, fine, in this range. So now this is your balanced tree. Okay. So which rotation you have performed here? You have performed here the right rotation. Fine. Okay. So this is your LR problem solution. Okay. Now see here, we have discussed the all the 4 types of problem. Okay, so we can get only these 4 types of problem. Okay, either your RR problem, LL problem, or your RL problem or LR problem. Because of these 4 problems only, your tree will not be balanced, and then we have to solve these problems by doing the rotation to make the tree our balanced tree. Okay, now see here, when we are having a RR problem, then what rotation we are performing? Left rotation. So whenever you have RR problem, so you have to perform opposite. If the problem is right problem, RR problem, then you have to perform left rotation on it to make it balance. If you are having LL problem, then what you have to do? Right rotation. Okay, so for LL you have to perform a right rotation to make it balance. If you are having your RL problem, then what rotation you have to perform? See, RL, so you have to think like this, that I have to make it either RL or LL only. Okay, because for that we know the rotation. Okay, now see, this is already your R, so if I will make this also as R, then I can perform for RL, we can perform left rotation. So what I will do, I will perform a, for this I want to make it RR, but this is on left. So for left, what rotation we have to perform? Right rotation. That opposite you have to remember. If it is left problem, you have to perform right rotation. If right problem, then you have to perform left rotation. So this is your L. So this you have to perform a right rotation. For right rotation, this 5 will come here, 7 will come down. Okay. Now this will become your RR problem. Now for RR problem, you know, if it is RR problem, then you have to perform the left rotation on your RR problem, and now you will get your balance tree. Now same for this LR problem also. See, this is your LR problem, but you have to make it either LL or RR problem. Okay, now L is already this one, so this R also you have to make it L. Okay, so for this you have to perform, when it is R problem, you have to perform left rotation. So you will move the tree to the left side. So when it will do left, so 5 will come above, 1 will come down. So it will become like this. Now it has become your LL problem. Now for LL, you know, if it is LL, then you have to perform right rotation, and now this 7 will come down, 5 will become your root node, and 1 will come here. So in this way you can solve your these 4 types of problems. So see what we can see here, that basically you have only 2 types of problem, LL problem and your RR problem. Okay, so basically you have only 2 types of problems. Okay. So okay, I will write here. So basically you are having only 2 types of problem. One is your RR problem. Okay, one is your RR problem, and the second one is your LL problem. Basically you have these problem only, because LR and RL also you have to make it either of LL or RR only. Okay, so basically you have 2 types of problem, and the solution for your RR problem is what? For RR problem, if you are having, then you have to perform the RR problem, you have to perform the left rotation. For RR problem, you have to perform the left rotation, and for LL problem, you have to perform the right rotation. Fine. So these 2 things only, the overall summary, this only you have to keep in mind, that we have basically only 2 types of problem. R means R is there, so we will perform opposite of it, that is left rotation. If it is L problem, then we will perform the opposite of left, that is left is right, so we have to perform the right rotation on it. Okay, so you see, this was basically your all 4 types of problems and their solution. Fine. So see, what we have learned in this video is, okay, see, first of all we have learned that, what we have learned in this video, see, first of all we have learned what is your AVL tree. Now you know AVL tree is your binary search tree, but that is your balanced, that is your height balance. Okay, this we have learned, that is your height balance. Okay, after that we have seen that what is the meaning of height balance. Height balance means that both the height of left subtree and right subtree should be almost equal. Okay, and almost equal means that it can be either exactly equal like this, or then, or it can be one more, left subtree can be one height more than this one, or right can be one more height than your left subtree only. Okay, so your balance tree can either have these 3 ways, or then only your balance factor, I have told you that it is falling under these 3 value. 0 when your tree is completely balanced, that is left and right height tree is exactly equal. When it is -1 and 1, we have discussed that when the left is 1 more and right is 1 more. Okay, so we have learned that in this our balance factor is the most important thing which will tell us about that our tree is balanced or not, and that we have to calculate for each and every node. Okay, so to check that which node is our not balanced. Okay, then after that we have seen that we are getting the 4 types of problem: LL problem, RL problem. Okay, LL problem, RL problem, RL problem, and your LR problem. And finally we have defined those under 2 basic problem: RR problem, LL problem. And for RR problem your solution is left rotation, and for your LL problem the solution is your right rotation. Fine. So now I hope you understood all this. Okay, so still if you have any doubt, please comment on our comment section. Thank you.